Okay, so let's talk about central limit theorem. The theorem says that a sample mean, your random sample mean, would be approximately normal when your sample size is large enough. Or technically, that let xi be a size n random sample from a population. Okay, here the population distribution is unknown to you. We do not say it's normal or not. From a population with mean mu and standard deviation sigma. If we let x bar n to be our sample mean, then as long as the variability of population is finite, then when your sample size goes larger, and larger, your sample mean would be closer and closer to a normal distribution. Okay, that's what we get from central limit theorem. So it basically just means if you have a population and your sample size is large enough, you can say your probability distribution of the sample mean is normal. Okay, you just need a very large sample size. So we have no reason to prove it here, but let's get some ideas with experiments. Consider our old friend the wholesale data about fresh food in the data set. Okay, let's try to use it as our population. So if we draw the histogram for those fresh food sales, then we can see a very non-normal distribution. The distribution is highly skewed to the right. Okay, the peak is here. You don't even have any left tail. You only have a very long right tail. So that means your distribution is no way to say that the population is normal. And then let's do the experiment about each time I'm going to select n sample. Okay, I'm going to randomly collect n values from that around 440 values from my population. So for example, I may calculate the sample mean for a sample size of 2, sample size of 5, or sample size of 20. So that means this is just the histogram, the same as from the previous slide. Here, this is I randomly select 2 values out of the 440 values. Once I get that 2 values, I calculate their sample mean. Okay, and I repeat this 5,000 times to get 5,000 values for sample means, and then draw a histogram. That helps us to estimate what's the distribution of the sample mean. When n is 2, well, still not really like a normal distribution, but we can see the curve, the peak somewhat shifts to the right, and now we have a tiny left tail. When n is 5, then it looks again even more like a balanced distribution. When your n is 20, then we can see that this is somewhat very close to a normal distribution, right? So when the sample size n is large enough, the sample mean is approximately normal. And when n becomes larger, okay, when n becomes larger, the distribution of sample mean becomes more and more like a normal distribution. And that's the point here. When you have a non-normal population, but your sample size is large, then your sample mean would still be close to its midpoint and following a normal distribution. The idea is still the same. If you want your sample mean to be very large or very small, you need most of its values to be at the same direction. All of them are large, or most of them are large at the same time, or most of them are small at the same time. As long as your sample size is large enough, that's not going to be happen with high probability. then it's not so hard to do the prediction, then it's basically normal. When your population is not so skewed, for example, when it is in uniform, the sample mean would still get to normal when n is large enough. For example, we may consider the values in the fresh sector that are less than 1 at 10,000. Okay, then the population would be like this. It's basically very close to a uniform distribution. In that case, when your n is 2, it looks like a triangle. When your n is 5, or even if n is just 5, this guy looks very close to a normal distribution, right? And when n is 20, your sample mean is almost a perfect normal distribution. You can even feel that this distribution is symmetric, right? So that means we only need a small n for the sample mean to be normal. When your population is quite skewed, you need n to be larger. When your population is somewhat closer to uniform, you only need a smaller n. And if your population itself is triangular or is close to normal, then your n can be even more smaller. And finally, if your population itself is normal, then no matter how many values you get in a random sample, your sample mean would be normal. Okay? So in short, the central limit theorem says that for any population, the sample mean will be approximately normal as long as the sample size is large enough. Without the distribution of the sample mean, with the distribution of the sample mean, we may then calculate all the probabilities of interest. So this theorem is so powerful in the case that, in general, why do we need to rely on sample? Typically, it's because we know nothing about the population, and that means we do not know whether the population is normal or not. Okay, so it's hard to say whether the population is normal in general, but if you just want to apply the central limit theorem, you don't need to know it. Central limit theorem applies to any population. Okay, so very quickly, let's make a summary. You have two ways to say that your sample mean is normal. Okay, there are two ways to say that. Either your population is normal, or your sample size is large enough. Okay, and how large is large enough? In practice, we typically use 30 to be the criteria. So let's put 30 here. Okay, so either you have a small sample, but from a normal population, or you have any population but your sample size is greater than or equal to 30. In either case, it's safe to say your sample mean is a normal random variable, and then you can do all the calculations you need. Okay, that's central limit theorem. Thank you.